In this lecture, we will be seeing the formal definition of Turing machine. In the previous two lectures, we have seen an introduction of Turing machines, and now we will see how can we formally define Turing machines. So a Turing machine can be defined as a set of 7 tuples, namely Q, sigma, tau, del, Q0, B, and F. Now let us see what these tuples mean. First of all, we have Q, which is the non-empty set of states. So as you know, Q is always used to represent the set of states, even in finite state machines and push-on automatas also. Q was the tuple that is used to represent the non-empty set of states. So that is the same even in case of Turing machines. And then we have sigma, and sigma also, just like the other machines that we have, it represents the non-empty set of symbols, or we can say it is the set of input symbols that we have in our Turing machine. And then we have tau. Now tau is something different from finite state machines and push-on automata. And what is it? It is a non-empty set of tape symbols. So when we studied the introduction of Turing machines, we saw that Turing machine has something known as the tape. What is a tape? It is a infinite sequence of symbols. So those symbols, that means the tape symbols, they are represented by this tuple tau. So it is a non-empty set of tape symbols. And then we have del, which is the transition function. And we know that transition functions are there even in finite state machines and push-on automatas. And they are defined in different ways according to how the machines work. So in case of Turing machine, we have the transition function del, which is defined like this: Q cross sigma to tau cross R or L cross Q. Now let us see what this actually means. So we know that in Turing machine we have states, and then we have our input symbols, and we also have the tape symbols. And here this means that when we are on a particular state, on getting a particular input symbol, we write something into the tape sequence, and we move either right or left on the tape, and then we go to the next state. So that is what we mean by the transition function del in Turing machine, because that is how the Turing machine actually takes transition from one state to another. So this will become more clear when we take our examples. And then we have Q0, which is the initial state. So Q0 is the initial state or the starting state. And then we have B, which is the blank symbol. So if you have seen the introduction of Turing machines, which I have already discussed, we saw that in the tape we have a special kind of symbol known as the blank symbol. And what is the blank symbol? It is a symbol that is used for filling up the empty spaces in our tape sequence. And then we also said that this blank symbol does not belong to the set of input symbols that we have. That is why I said blank is a special symbol, and that is why we have a different tuple that is used to denote the blank symbol, which is B. And then we have F, which is a set of final states. So even in the introduction I already discussed that in Turing machine there are basically two kind of final states. One is the accept state and another one is a reject state. So F represents the set of final state. So these are the 7 tuples that are used to define a Turing machine. Now let us see how we can write the production rule of Turing machines. So the production rule of Turing machines can be written like this. And what does this mean? This means that initially we are in the starting state Q0, and on getting a particular input symbol, it could be anything. So we just represent it by A over here, and on getting this particular input symbol, it goes to another state Q1 and it writes the symbol Y onto our tape, and then we move either right or left on our tape. So here it says it is moving right. So this is just an example, and it shows basically how the production rules of Turing machines are written. So even when I explain the transition functions, it should be clear to you how the transitions are taken, and if you understand this, this production rule will be clear to you. Now the next thing that we need to discuss about is Turing's thesis. So let us see what this Turing thesis says. Turing thesis states that any computation that can be carried out by mechanical means can be performed by some Turing machine. So Turing thesis says that if there is any computation that can be mechanically performed, then that computation can also be performed by some Turing machine. So from this you can understand how powerful a Turing machine actually is. So we have discussed about other machines in this course of lecture series, like finite state machines and push-on automatas, and we saw that how limited they are and what are the limitations that they had. But seeing this Turing thesis, you can understand how much more powerful a Turing machine is as compared to finite state machines and push-down automata. Now, this is the Turing thesis that we have, and there are few arguments for accepting this thesis. Now let us see what are the arguments that are used to accept or support this Turing thesis. Number one, anything that can be done on existing digital computer can also be done by a Turing machine. So any computation that we can do on an existing digital computers that we have today, that can also be done by a Turing machine. So we see how powerful Turing machine is. And then number two, no one has yet been able to suggest a problem solvable by what we consider an algorithm for which a Turing machine program cannot be written. So this means that if there is a problem that you have, and if you are able to write an algorithm for solving that problem, then you will also be able to design a Turing machine program which can be used to solve a same problem. So till now nobody has been able to suggest any such kind of problem whose algorithm can be written but cannot be solved by a Turing machine. That means if you are having the algorithm, if you are able to design the algorithm for a problem or for solving a problem, then that can also be solved by a Turing machine. So that again shows how powerful a Turing machine is, and these two arguments, they support our Turing thesis, which says that any computation that can be carried out by mechanical means can be performed by some Turing machine. So that is about the Turing thesis. Now let us see what are the languages that can be accepted by a Turing machine. So the languages that can be accepted by a Turing machine, it is known as recursively enumerable languages. I have discussed this even during the introduction, and it says that a language L and a set of input symbols sigma is said to be recursively enumerable if there exists a Turing machine that accepts it. So if a language is acceptable by a Turing machine, then that language is said to be a recursively enumerable language. So we know that we have discussed other machines like finite state machines which accepts regular languages, and then we discussed about push-on automata which accepts context-free languages, and then Turing machine, it accepts recursively enumerable languages. Now when we talk about these languages, there are some other classes of languages that we need to discuss, like Turing recognizable languages, Turing decidable languages, and also languages that cannot be recognized or decided by Turing machines. So those things we will do a separate lecture for that, and when you understand what is Turing machine and what are the classes of languages accepted by Turing machines, those classes of languages later on will be very easy for you to understand. So first of all, we will try to understand how Turing machine works and what are the kind of languages that is accepted by the Turing machine. So in this lecture, we have studied about the formal definition of Turing machines, and we also saw the Turing thesis, and we also saw the languages accepted by Turing machine, which is the recursively enumerable languages. So from the next lecture, we will be taking examples of Turing machine where we will see how Turing machines are designed and how they